Okay, I'm just going to go through bending moments and how to take bending moments about a point so we can find the reaction forces. As some people, I think, would quite like a refresher on that. So, first of all, don't panic. This is my useful wiki, which hopefully most of you know by now. You can find on bit.ly/S teacher. Okay, so just going to do a quick reference. We've got 10 plus 1 steps to bending moments. Okay, so first of all, here are the 11 steps, and we'll go through them in a little more detail. Select the point we're taking moments about. Sort out our UDLs. Identify clockwise and anti-clockwise moments. Take the clockwise moments and the anti-clockwise moments. Remember that for equilibrium, the clockwise moments must equal the anti-clockwise moments. And then we'll have an equation which should have only one unknown in, probably reaction force 2. So we can rearrange that equation to find our unknown equation, our unknown variable. And then finally, we don't have to do all of this again. We don't have to do all of this again to find the remaining reaction force, because we know that the up forces must equal the down forces for equilibrium. Remember our three rules for equilibrium are that the up forces must equal the down forces, the left forces equal the right forces, and the clockwise moments equal the anti-clockwise moments. And if all those three things are true, then what we've got is in equilibrium. Okay, so we can use that. So we can say, well, the up forces must equal down forces. Well, the only force we won't know on our beam now is the remaining reaction force. So we can add all the up forces together, which is reaction force 1 plus reaction force 2, and all the down forces together, which is all our loads. Then we can just rearrange that quite simply, and it's a simple subtraction sum then just to find our remaining reaction force. So let's just step through this in a little bit more detail. So here we've got quite a complex looking beam. We've got a UDL, we've got 2-point loads, and it's not symmetrical. So moments can be taken about any point on the beam, but since all the dimensions come from R1, let's make life easy and call R1 Bob. Now we've not got any dimensions on this drawing yet, but here's one I prepared earlier. Okay, so let's have a look at that. I've put all the dimensions on here, so it's 1.5 meters to the start of the UDL, 3 meters to the end of the UDL, 3.5 meters to the 10 Newton point load, 4.5 meters to the 12 Newton load, and 5 meters from R1 to R2. You can see me flouting BS 8888 conventions there by putting the dimensions below the line. We all know the dimensions should be above the line, don't we? So, every day's a school day. So it says here, sort out the UDLs. Well, I can't remember what UDLs are. Uniformly distributed load. And at this stage, a little trickier than a point load, but don't panic. Our aim is to make it a nice, simple point load. So if it were 1 meter long, it would weigh 6 newtons. If it were 2 meters long, it would weigh 12 newtons. So all we do is multiply the newtons per meter by the length of the UDL to get the equivalent point load. Okay, and then we place it at the midpoint of the UDL. So it's the middle point of the UDL, not the middle point of the beam, but the middle point of the UDL. Okay, so let's see how that unfolds then. So let's have a look. It says the UDL starts at 1.5 meters and ends at 3 meters. Starts at 1.5, ends at 3 meters. So we can work out it's 1.5 meters long. The 8 Newton meter load gives a total of 1.5 meters long times by 8 Newton meters equals 12 newtons. So this is the equivalent point load that needs to go at the midpoint, halfway along the UDL. So it needs to go, I don't know if it's recording my cursor. No, it's not recording my cursor. That would be too easy, wouldn't it? So it needs to go about halfway along the UDL. Let me just see if I can set up cursor for me. Okay, it should be capturing my cursor. Let's hope it is there. So there, that's what we're looking at just there, the midpoint. So if it's 1.5 meters long, well, half of 1.5 is 0.75 meters. And so we put the equivalent load, 1.5 plus 0.75 meters along the beam. Okay, so that's 2.25 meters from R1, which we've called Bob. There we are, we called it Bob just there. Yeah. Hi, Bob. And right, so there we go. Okay, so hopefully, and here you can see I've removed the UDL and I've put the equivalent point load in place. Okay, so this is all just to find the reaction forces. Okay, obviously when we get to doing bending moment diagrams, things get a little bit more complicated, but we won't worry about that for now. So there we are, we found Bob. We found the point load. So 2.25. Okay, so would we like to know more? Heck yeah. So this is step 3. Identify the clockwise moments and the anti-clockwise moments. So label in your diagram. So you can put a little arrow, or you can put CW and ACW, just to help clarity of thinking. And don't forget that reaction force. Yeah, some students do. They forget your reaction force there. You've got to remember that even though we don't know what it is yet, it is still a force and it's acting upwards. Okay, so that would be an anti-clockwise. And if you're struggling with this, I suggest that you hold a pen. If you hold it loosely in one finger at one end, and then you can push down on your pen or up on your pen and see which way your pen rotates and where your finger is. That's where you're taking moments about or bob. Yeah. So would you like to know more? Oh yes. Oh yes. So we take the clockwise moments. So what do we do? Well, a moment is a force times by a perpendicular distance. So the force is 12 and the perpendicular distance to the point we're taking moments about is 2.25. But we've got 1, 2, 3 clockwise moments. So we need to add those moments together. So that's 12 times by 2.25 plus 10 times by 3.5 plus 12 times by 4.5. So let's see what that looks like. So I've just done them separately there. We've had them all together, and that gives us 160 newton meters. And it says here we usually do 4 to 7 in a single step. So we'll come back to that in a moment and see what that looks like. So yes, we'd like to know more. Okay, so take the anti-clockwise moment. So we've only got one anti-clockwise moment here, and that's R2, and that's 5 meters away from Bob. So we've got 5 times by R2, our force times our distance, or R2 times by 5, force times distance. Yeah. So let's see what that looks like. It looks like 5 times by R2. Okay, so multiply each force by its distance from Bob, add these together. So in this case, we've only got the one. And that's often going to be true, but might not always be. Okay, let's move on. And so now we say, well, our clockwise moments equals our anti-clockwise moments. Okay, so this is what we found out from step 4. It was 116. And then from the last step, we got 5 times by R2. Okay, so we can just very easily rearrange that to find the unknown, and then R2 is 23.2 newton meters. Okay, so they're usually done in a single step, so let's see what that looks like. What that looks like is this. So here, instead of us having each little sum on its own line, we've just put them all together and we put them in brackets to indicate that we do the thing in brackets first and then have them all together, and then we've got the anti-clockwise moments on the other side of the equation, so 5R2. Okay, but hopefully you can see it boils down to the same answer here. All right, so let's just close that. Okay, so let's carry on. So now we're on to steps 8 to 10. Okay, so for equilibrium, forces must be equal and opposite. So all down forces in the beam must equal all the up forces in the beam. So we add all the up forces and all the down forces together. But we don't add the up forces to the down forces. We just add the up forces to the up forces and the down forces to the down forces. So that's what we're doing here. Going down, we've got 12 plus 10 plus 12, which equals 34. The total up force on the beam is reaction force 1 plus reaction force 2. And so reaction force 1 plus 2, 3. So we're just putting reaction force 2 into that there. Okay, so we say up equals down. So reaction force 1 plus 23.2 must equal 34. And so, you don't even have to rearrange that. You can do that in your head more or less, can't you? Yeah, so, 34 minus 23.2 must equal reaction force 1. That's it, and that's how we use bending moments to find reaction forces on simply supported beams. Okay, thank you very much.